Hi, my name is Ioannis Anifantakis. I come from Greece. I work in Deloitte Digital. Um, this talk today is the result of, let's say, an personal investigation I have done. I'm not working on the Android open source project. However, I was always intrigued about how things happen internally. So that made me search like how things work. My first thing was like, what the heck is the context? So everybody was passing the context without knowing why. So I was like, okay, what it is, what it really is, nothing ever fitted. So I started making my own research, and I ended up with this article that I have on Medium, which is like how the context and the manifest, they work together. And it was really my first, let's say, research about the Android internals. After that, I searched a little bit more because the context provides you like something on the surface, you understand what's happening, but then I want to see what happens deeper inside. So this is another article that is, let's say, the source of today's talk. So based on this, we will see now what happens after we use the context, how internally the Android operating system handles things and how it makes inter-process communication and so on. This we will try to avoid at all cost coding. We will see this as a documentary, let's say. It will be, let's say, the National Geographic of Android internal, so we will see how things work on the inside and from a high level, okay? So let's start by the question, like, what happens when we tap an icon of an application, all right? So what happens when you install an application? Now, when you install an application, the app is given its own unique Linux user ID, and it is set to run on its own instance of the Android runtime. Thus, each application is completely isolated with all its resources inaccessible to every other application. Then, when we run an application, it is restricted from constructing and managing its own components and accessing even its own resources by direct code. Yes, even for the resources, we have to ask the context to get a resource back. So instead of that, it depends on requesting the Android system to do all that on its behalf. Now, overall, this isolation approach promotes a more secure environment for your application due to leaving much of the responsibility to the operating system rather than to developer code. But if the Android system is that restrictive to its application, that raises two issues that needs to be addressed. So, firstly, need a way to communicate with the Android system so they can request it to construct and provide the components and resources on their behalf that would be otherwise inaccessible directly by code. And secondly, the Android system should keep track of those installed applications and their components in order to be able to launch and provide them back to the caller when that request fits their existence. Now, to address the above problems, the context and the manifest, respectively, come to the rescue. And as you can see, there is an obvious correlation between them. So let's say a few words about the manifest before we go to the internals. Now, all Android developers should be aware that every Android app they have is accompanied by an Android manifest XML file, yeah? Now, when you create an application, the Android system really knows nothing about it unless it's posted at the application's manifest file. It's the registry of your Android app. So now inside the manifest tag, you will find several child tags, like the permissions by using the uses permission tag for Android to know what restricted hardware and software resources should be made enabled. and also any custom subclass implementation of the 4 application components you wrote inside your application. For Android to index them so that it can provide them back to the caller application when it fits their existence. So now these would be activity tag for activities, their service tag for services, provider for providers, and receiver for broadcast receivers. Now, there is a reason we call this the 4 application components, and it is because out of all the custom classes that we create in our code, only those 4 classes need to make their presence known to the Android system. It's the components that the Android system needs to know how to handle. If you have, let's say, a Ktor library, this runs inside your running activity, for example, you handle it. But if you need to inflate something, you need to ask the operating system to do something on your behalf, then those things need to be registered so that the operating system needs to know how to address them. Okay? So these are the 4 application components. Now, these there are some context and some non-context components. Now, as you will see, the blue ones are the context ones, and the green ones are the non-context ones. So as we can see, activity, application, and service, they are direct descendants of context. And especially activity is wrapped inside the context team wrapper, which wraps the context wrapper, which wraps the context impl. Okay, so in fact, the activity has this UI theming available, while the application and services, they do not. Now, the content provider and the broadcast receiver, they receive a context to get their job done, but they are not context descendants, because only the context descendants are actually having a life cycle. So when we have a context, our components, they gain life cycle. So for the manifest TLDR, now the manifest notifies the Android system of the application's own existence, any permissions needed, and any components of your application. All right, so all this approach yields a richer user experience due to other application components becoming available to your app, or your application components becoming available to other apps. Okay. So now let's come back to that previous slide and talk about the context. So we saw how the manifest can expose components to the Android operating system, but now for the context, we said that it's the handle to the Android system, and that's exactly what it is. The context is the badge that your code shows when it asks the framework to do something privileged on your behalf. You use it to start an activity, bind a service, send a broadcast, or just fetch a system service. But context is not about how the results and the life cycle come back to you. The life cycle and other instructions come back over from a different line that we're about to meet now. So let's explore the hidden ecosystem. So let's do the National Geographic of Android that we said earlier. Okay, so let's start with the inter-process communication. So for context to communicate with distant processes, we utilize Android's core inter-process communication IPC mechanism, which we call the binder framework. Now, binder is a framework, as we said, that provides inter-process communication between Android components. However, we call it a framework because the binder does more than just being a message pipe. In mobile environment, that requires extra security and resource handling. The binder is a full RPC runtime. It packages your call, delivers it to another process, brings back the results, checks who's calling your application's ID, enforces permission, watches if other side crashes, and cleans up afterwards. So in short, the binder is the secure cross-process calls mechanism suited for the Android needs. So we mentioned RPC, and we said that the binder is a full RPC runtime. So let's see what an RPC really is. An RPC, which means a remote procedure call, is an interface layer that allows code to invoke methods in different processes as if they were local. So while running within the inter-process communication transport, okay? So we use the IPC, inter-process communication, to communicate in a local-like way through RPC. Okay. Now on Android, these RPC interfaces are typically defined in AIDL, IDLE, the Android Interface Definition Language, which generates binder stubs and proxies that run on IPC calls. Now, many system services hide their idle interfaces behind higher level manager classes, which is why those feel local. For example, the activity task manager, which we're going to see later, it's accessed via the activity task manager, which implements it. Package manager from application package manager, window manager via window manager, and so on. But you can also define your own AIDL interfaces to communicate across processes. Now, common cases include media engines, companion apps, and vendor plugins. Like sometimes you have seen companion applications that give, for let's say, just for Samsung devices, some extra characteristics to the main app. So they say, download this plugin app, okay? This plugin app uses idle to provide hardware-specific features to the main app. Okay, so that way you can use idle yourself. However, of course, for simple cases, broadcasts and content providers are the way to go, but if we need some continuous communication, yes, we can use our own idle. So, as a takeaway, the binder is Android's IPC transport and runtime, while the idle is the interface definition layer that defines the RPC contracts that run on top of binder. Okay? Now, one example here is this, using the package manager. As you will see, it feels like a local call, but in fact, our application uses the application package manager behind the scenes, and then we have the stub through the iPackage manager interface, which is actually the binder call, okay, that calls the package manager service. So this is an example of an idle. Now, let's talk about the system server. The system server is actually the long-lived Java process that is forked by Zygote during early boot. It's one of the most critical processes that Zygote spawns. It hosts core framework services like Activity Manager Service, the AMS, the Activity Task Manager Service, which is the ATMS that we will meet next on the next slide. Now, these services expose binder interfaces which are defined in idle, so apps can call into the operating system. Among them, the iActivity Task Manager, which is implemented by the ATMS, which serves as the entry point for activity and task operations. Now, those services implement the idle defined binder interface and expose them via the service manager. But let's take a look how this works. Let's take a look at the AMS and the ATMS objects that live inside this system server process that is forked by Zygote. So, historically, the Activity Manager Service, or AMS, was Android Framework's central nervous system, coordinating activities, services, broadcast receivers, and content providers, and also the creation and the teardown of application processes. But as Android evolved, in Android 10, that is API level 29 and on, Google split some of those responsibilities that originally existed in AMS into the new service that we call ATMS. So, Activity Task Manager Service, the ATMS, took over the user-facing duties of AMS, such as managing activity lifecycles, orchestrating the backstack, and organizing tasks on screen. It's the binder entry point for activity operations through the iTask Manager idle interface. And it drives activity lifecycle by sending client transactions to application thread. Now, you can think of the ATMS as the front office dealing with everything the user sees. And now, for the AMS, it still exists, but it now focuses only on process and application lifecycle. Application lifecycle, not activity lifecycle, application lifecycle, process lifecycle, okay? And the overall application state. So you can think now of AMS as the back office and the resource manager. It is the guy that requests the Zygote USAP to start processes and kill processes as needed. It manages activity components, services, broadcasts, and content providers. Now, for AMS and the ATMS, well, ATMS owns the activity task surface, while the AMS supplies and governs the process that runs it. So now that we have this glossary, we can now very fast take a look at how the application communicates with the system server process and how the system server process communicates back to the application. Now, they both communicate via the idle exposed interfaces. So, starting with the iActivity Task Manager interface, as the name suggests, this is implemented by the Activity Task Manager service, ATMS, in the server, in the system server, and it's the interface that your application uses for identity. Now, when your application calls start activity, the SDK invokes iActivity Task Manager in ATMS. ATMS resolves the intent, validates the permissions and the policies, and applies task and backstack rules. Now, if the target process is not running, ATMS asks the AMS, which is the back office, to ask Zygote to create a new application. So whatever we do from the ATMS goes to AMS, and then from AMS to Zygote if we need inflation. Then, now it's the iApplication thread. And in the iApplication thread that lives inside your application at the activity thread, the direction reverses. So this is when we want the system server process to communicate to your actual process. So your process now doesn't pull a lifecycle, it receives it, as you see. The activity thread via its inner application thread, which implements the iApplication thread interface that we see over there, executes the incoming instructions from the ATMS that arrive from the system server process. For activity lifecycle, the ATMS sends a client transaction, which in fact a client transaction that we also mentioned earlier is a structured envelope of callbacks plus final lifecycle states to the iApplication thread scheduled transaction, which activity thread processes on the main looper. So iActivity Task Manager versus activity thread that we saw earlier. In other words, iActivity Task Manager is how requests leave your process to control activity operations, while iActivity thread is how the results and lifecycle arrive back to be executed inside your own process. Now, about the activity thread. Activity thread now is a non-public class, okay? It's actually, we talk about this thing here, okay? The activity thread that runs inside your application. Now, it is a non-public class that runs inside your application process, acting as the executor for the commands that the ATMS and the AMS send to it, okay? And despite its name, that it's activity thread, it's not just for activities. Now, while you will never directly interact with activity thread, your application code, it still plays a very important role on the inside. It's the main thread manager, okay? It is the one that creates the looper and sets the message queue. It's the process initialization. So when Zygote USAP specializes, which we will see later, your application process, the system invokes activity thread dot main, which sets up the main looper. It's the component lifecycle orchestration because it receives the lifecycle commands from the system via client transaction envelopes, as we mentioned. and it sets up the context. It creates the context that the objects use. Okay, so activity thread is also some very important part of our application. Now, let's see that now that we have the glossary and have talked about some terms like what happens on the background, we have the system server, that process that hosts the AMS and the ATMS. Now that we discuss how AMS and ATMS talk through application thread with our process, now let's look at this again from a higher level. So, step one, when the user taps your icon, the launcher just calls start activity like any other app. That call crosses our front office, so it goes to ATMS inside the system server. Then the ATMS resolves the intent details like which activity class, in which package, for which user, and so on, by consulting the package manager. Now the ATMS asks a simple question to the AMS, to the back office, which is the source of truth for the running processes. Is this app's process already running? If yes, great. We just show it immediately. Otherwise, the ATMS will then ask the AMS, which is the back office, as we said, to bring up the new process. Well, in that case, in this step, the AMS takes over and it looks at your manifest and settings. Then it talks to Zygote, which we will see later, over its socket and says, please fork me a child for this package and for this user. Then the Zygote either forks right now or hands back a USAP. We will see Zygote USAP later, okay, which is an unspecialized app process from a worm pool. The new child then, it gets specialized. It gets the application's user ID, group ID, SC Linux domain, mount storage namespace, everything actually that builds your sandbox. Then the activity thread main gets called, and that method becomes your main UI thread. Now, after the second step, we get to the third step. Now, in this step, where all work happens to create the application context. Okay. Now, inside the brand new process, activity thread main sets up the looper and the message queue, which is your UI thread, as we said, and we get the heartbeat of our application. Then the application announces its presence to the system by attaching itself to the AMS, so that the AMS knows of the process existence. The AMS, which is the back office, needs to know which applications exist because it can kill running processes. So at that point, the AMS knows of the process existence. So the AMS responds with a bind application instructions. That's a single big message containing everything your process needs to become your app. The runtime loads application code and creates the application by calling the make application function. And a new context impl is created for the application and wired as the application context. Now, this is the point, the last point, where the application onCreate is called. So when you define your custom class that extends application and you have the onCreate for your application, this is the last step. And as you see, this is before any activity gets to live. So after that, at the last step, that is step 4, it's where the actual activity creation happens. Before we talk about how activity creation happens, you came to appreciate that we say that things that we really need to initialize before any activity or anything happens, it happens at the last step of the previous slide. Okay? So after this now, the ATMS, which is the front officer of the system server, schedules a client transaction to the application's iApplication thread. So it sends to the application thread information to launch the activity. Then the activity thread class handles everything to create a new context impl for the activity. The context impl gets customized with context theme wrapper, and the activity receives a specialized context through the activity attached. And then the normal life cycle begins. Now, I need to make clear, we said many times context impl, but I never explained this. So context impl is the actual implementation of your context. You never really see it, it's encapsulated. What sits on top of it is the context wrapper, okay, that gives the extra features we want, not the extra features, that's what we interact with. And that can further package into context theme wrapper if we want to attach theme information. So that concludes the process that happens behind the scenes when we run our application. What we haven't discussed yet, though, is the Zygote, which is actually the mechanism that really gives birth to an actual application. So we said that we create a process, but we didn't see how we create it. Now, the Zygote is the way that it's being created. And for that, I want to invite Salvatore, a good colleague of mine, to say a few words about the Zygote. Thank you, Salvatore.
Thank you. So every Android process starts from a single parent cell called zygote. The name is taken from biology, where the zygote is the first cell of the human body. It's the fertilized egg that eventually will become a person. The slides. Yeah. So when your phone boots, Zygote is launched very early, before any user app exists. During this first moment, it preloads a massive amount of Android DNA. It initializes the Android runtime, ART, in its own process and preloads core, Java, and Kotlin libraries, together with the system resources and important classes, like, for example, context simple or activity thread. All of these are kept warm in memory and ready to use. So, when you tap an app icon and ATMS, the Activity Task Manager service, realizes that your app process is not running, it doesn't launch a new runtime. It simply asks Zygote to fork. So, you can imagine Zygote as a process photocopier. It seems that instantly creates a perfect copy of itself. But that's just an illusion, because fork uses copy on write, cow. So, at the moment of forking, no actual memory is duplicated. Zygote is not actually copied. The new child process shares all the read-only pages, so framework classes, boot image, and resources with its parent, Zygote. Only when the child needs to modify something, so for example, when it needs to write to the heap, then a copy of that page only is duplicated. This means that all the read-only pages can be shared by hundreds of apps without wasting space. These architectures enable very fast app startup with low memory use, because every new app process forks from Zygote instead of reinitializing the runtime and the framework from scratch every time. The result is near instant process creation with huge memory savings. Before Android 10, every new app launch required Zygote to fork on demand when you open the app. It was fast compared to traditional process creation, but there was still the latency of asking Zygote, forking, and specializing synchronously at the moment of the tap. Android 10 introduced USAP, unspecialized app process. So instead of waiting for a user tap, the system pre-forks a pool of neutral processes in advance. These unspecialized children have all the framework classes preloaded, but no user ID, no group IDs, no security enhanced Linux. Now, to picture how this works, let's switch to a more fun metaphor that really fits the Android personality. If you ever watched the movie Despicable Me, you already know its army of yellow helpers, the minions. So, you can imagine the Zygote as Gru, the head scientist, and the user pool is a group of yellow minions hanging around the lab. identical, cheerful, and always waiting for orders. When you tap an app, one of these yellow minions is instantly called to duty. So the pool is constantly maintained. As soon as a minion is specialized and leaves the lab, Zygote asynchronously creates a new minion to keep the pool full, tuning the pool size based on memory pressure and launch frequency. Then there is specialization. So the process receives a unique Linux user ID and group IDs, which sandbox it. The kernel assigns a security-enhanced Linux context, mandatory access control rules that define what the app can and cannot touch. Android configures the mount namespace and environment variables. Finally, Zygote tells the child to run activity-thread.main, which set up the app's main looper and message queue. The purple minion is not just a copy, it's a fully specialized process. And only inside this specialized process, Android creates the real context that the developers use.
Dankeschön. Dankeschön, how do I say? Hello? Yeah, Dankeschön.
Thank you.
So, as you, this was concluding the, let's say, the mechanism that gives birth to our processes, which is, as Salvatore, my friend here, introduced to you. Maybe it's the most important of what we have discussed during this session, the effective and fast way to give birth to new processes. So that's on our side on this. And boom, here we are. Thank you very much for being here. Any questions maybe that we could possibly answer?